Hey, you ever just stop and think about what we even mean by common sense? Like, is it some sort of, built-in wisdom, or is it just the stuff we've gotten used to?
That's a great place to start. I think a lot of what we call common sense is really just our intuition built up from, well, our very limited everyday experiences.
Exactly. It feels totally obvious that space is, empty,
Hmm.
right? Or the gravity just pulls stuff down.
Hmm.
But today we're diving into how modern physics looks at these things. And spoiler alert, our basic intuition about the universe, it might be leading us way off track sometimes.
Absolutely. What feels right in our daily lives often just completely breaks down when you look at how things really work at a fundamental level. It's kind of like trying to understand the ocean just by looking at a puddle.
Yeah, and this isn't exactly a new thought, is it?
Hmm.
Einstein apparently said something like, common sense is just the prejudices we collect by age 18.
He did, and it's a powerful idea. Think about showing a smartphone to someone, maybe who'd never seen any modern tech. It would seem like magic, wouldn't it?
Totally impossible, yeah.
Right. Their common sense would say it can't happen. But once you understand a bit about, say, radio waves and electronics, suddenly it's not magic, it's just technology. It becomes common sense.
Okay, so understanding the physics behind things can make the impossible seem, well, less impossible.
That's the hope. Our goal today is to tackle some of these really mind-bending ideas and hopefully find those aha moments that stretch how you think about reality without, making your head explode.
All right, let's jump in. First up, dimensions.
Hmm.
We live in three spatial dimensions, right? Length, width, height. Easy enough. But physicists talk about more. Why is it so unbelievably hard to even imagine a fourth spatial dimension?
Well, fundamentally, our brains evolved to make sense of the world we perceive directly. We're wired for 3D.
Okay.
So, trying to genuinely visualize a fourth dimension perpendicular to all three of ours, it's like trying to imagine a brand new color you've never seen. Our mental toolkit just doesn't have that tool. A 4D object can't really fit into our 3D space in a way we can fully grasp.
All right, you can't pour a gallon into a paint pot, basically.
Mm.
Okay, the source material mentioned this character, Tread the Dot, living on a line. How does that help?
Ah, Fred. Okay, imagine a perfectly straight line. Fred's a point. He can only move forward or backward along that line. That's his whole universe, one dimension.
Simple enough.
Now, what if we curve that line into, say, a circle? Fred can still only move along the line, forward or backward. The path is curved, but he hasn't gained a new direction to move in. He's still stuck in one dimension.
Ah, okay, so curving the space he lives in doesn't automatically add dimensions. That's important.
Exactly. Curvature and dimensionality are different concepts.
Got it. And the source also defined dimensions by the number of coordinates you need to find something. Can you unpack that a bit?
Yeah, think about giving directions. If you're, let's say, on a barge stuck in a long, straight canal, I only need one number to know where you are, right? Like how far you are from the start of the canal.
Yeah.
One number, one dimension. Now, if you're out in the middle of a big, flat field, I need two numbers. How far east, maybe, and how far north from a landmark. Two numbers, two dimensions.
And for us, it's three numbers: length, width, height, or longitude, latitude, altitude.
Precisely. So the number of independent numbers you need to pinpoint a location tells you the dimensions of the space.
That makes sense. Okay, let's switch to space itself. Common sense says it's just emptiness. A big container for all the stars and planets and, well, us. Is that right? Just a passive void.
That's the intuitive picture, for sure. But physics pushes us beyond that. First, space can exist even if there's nothing in it. Imagine a totally empty box. If you could remove every single atom, the space inside, the volume, it's still there. It's the potential place for things.
So even if the universe was completely empty, space would still be.
That's the idea. It doesn't need matter to exist. But here's where it gets weirder. Thanks to Einstein, we know space isn't just a static background. It's dynamic. It can be warped, curved.
Whoa, hang on. Warped. Curved. How can nothing be bent? That feels wrong.
It's really tough conceptually. Think about drawing a square on a flat sheet of rubber. The square follows the rules of flat geometry.
Right. Angles add up to 360. Oh, wait, 90 degrees each? Yeah.
Right. Now, stretch or bend that rubber sheet. The lines of the square might look curved or distorted to us looking at the bent sheet, even though intrinsically they're still straight lines on that surface. It's the surface, the space itself, that's changing shape.
So massive things like stars and planets, they actually bend the space around them.
Exactly. They warp the fabric of space-time, and that curvature tells other things how to move. It's not just an empty stage. It's more like a trampoline surface that dents under weight.
Okay, the trampoline analogy helps.
Yeah.
Now, to help visualize this curved 3D space, the source uses this idea of 2D world. Flat people living on a flat surface. Why do we use that?
It's because we can't easily visualize our 3D space being curved within some higher fourth spatial dimension, so we drop down one dimension to make it easier to grasp the concept. Imagine beings who live entirely on a flat sheet of paper. They know forward, backward, left, right. They have absolutely no concept of up or down. That third dimension is as mysterious to them as a fourth is to us.
Okay, they're flatlanders.
Yeah. So if their flat paper world was actually, say, the surface of a sphere, they wouldn't perceive the sphere itself in 3D. But they might notice weird things in their 2D world because of the curvature.
Like what? How would they experience living on a sphere?
Well, for one, their universe would be finite. You can only go so far around a sphere, but it would have no edge. If they walked in a perfectly straight line, they'd eventually end up back where they started.
Whoa, limited but endless.
Exactly. And they'd do this without ever leaving their 2D surface. The inside of the sphere, that third dimension that causes the curvature, would be totally inaccessible, maybe even unimaginable to them.
Okay, that's a really neat way to think about it. And the source mentioned an explorer at the North Pole doing something with triangles. How does that fit in?
Yeah, that shows how geometry changes on a curved surface. Imagine starting at the North Pole, walking straight south to the equator. That's one side of your triangle.
Okay.
Then turn exactly 90 degrees, walk along the equator for a bit, second side.
Got it.
Then turn 90 degrees again and walk straight north. You'll end up back at the North Pole, completing the triangle.
Right. So 3 straight lines.
3 straight lines, yes. But look at the angles where you turned. You made 2 90-degree turns at the equator. And the angle back at the North Pole where the lines meet isn't 0. The lines come together. If you walked a quarter of the way around the equator, that angle at the pole is also 90 degrees.
Wait, so you have a triangle with 3 90-degree angles? It's 270 degrees, not 180 like in school.
Exactly. On a curved surface like a sphere, the rules of standard flat Euclidean geometry don't apply anymore. Triangles can have angles summing to more than 180. That's non-Euclidean geometry.
The geometry we learned is only for perfectly flat space. And our universe might not be perfectly flat on the grand scale.
Precisely. Our 3D space could be curved. And we can actually test this by looking at the geometry of the universe on huge scales, like measuring triangles made between distant galaxies. We don't need to see a fourth dimension to measure the curvature within our 3.
But on everyday scales, like my living room, it's basically flat.
Oh, absolutely. The curvature caused by Earth, or even the sun, is incredibly tiny on human scales. You'd never notice it drawing a triangle on a piece of paper. It's like trying to detect the Earth's curve standing on a football field. It looks perfectly flat.
Okay, that makes sense. One last bit on dimensions. The source contrasted moving outwards from the center of a circle versus moving up into a third dimension. What's the point there?
It's trying to illustrate what a fourth spatial dimension would conceptually be. If you're at the center of a circle on a table and move outwards radially, you're just moving within the 2D plane of the table.
Right, towards the edge.
But if you move up perpendicular to the table, you're moving into the third dimension. You're moving away from all points on that circle simultaneously in a direction that isn't outwards within the circle's plane.
Okay.
So, analogously, a fourth spatial dimension would be a direction that's mutually perpendicular to our length, width, and height. Moving in that direction would mean moving away from every single point in our entire 3D space at once. It's basically impossible to visualize, but that's the geometric idea.
All right, my brain is definitely getting a workout.
Oh.
Let's shift to gravity. The classic story, maybe true, maybe not, is Newton and the falling apple. What was his big insight?
Well, the key wasn't just that the apple fell. Everyone knew that. Newton's genius was realizing it was a mutual attraction. It wasn't just the Earth pulling the apple was also pulling the Earth.
Seriously, the apple pulls the Earth.
Yes. It's just that the Earth is so incredibly massive compared to the apple that you only see the apple move significantly. But the force is reciprocal. Newton's law described this universal pull between any two objects with mass.
So wait, right now my coffee mug is gravitationally pulling on my keyboard.
Yep. And the keyboard is pulling on the mug. And both are pulling on you, and you're pulling on them.
But the forces are just tiny.
Infinitesimally small compared to Earth's pull on everything, yeah. The strength depends on the masses and the distance between them. But technically, yes, everything pulls on everything else.
Okay, so that's Newton's picture. Universal mutual attraction. But then Einstein arrives and throws a spanner in the works, right?
Yeah.
With relativity and this principle of equivalence. What's that about?
The principle of equivalence is really profound. It basically says that you fundamentally cannot tell the difference between being in a gravitational field and experiencing acceleration.
How so?
Think about being in a really fast elevator when it suddenly accelerates upwards. You feel pressed down into the floor.
You feel heavier for a second.
Or in a simulator ride that spins you really fast, you feel pushed outwards. That feeling, that apparent force due to acceleration, is locally indistinguishable from the force of gravity.
So feeling pushed back in your seat when a car floors it, that's the same kind of physical effect as gravity holding me in my chair right now. That seems odd.
It does, but that's the core idea. Einstein loved thought experiments. Imagine you're in a sealed box, like a rocket cabin, with no windows.
Okay, I'm in the box.
Could you tell just by doing experiments inside the box whether you're sitting still on the surface of Earth, feeling Earth's gravity, or floating in deep space? But the rocket is accelerating upwards at just the right rate, 9.8 meters per second squared.
I guess.
Mm-hmm.
No, everything inside would fall to the floor at the same rate in both cases.
Exactly. You couldn't distinguish between gravity and acceleration. Or think about astronauts in free fall orbiting Earth, they feel weightless. That's the same feeling as just drifting in space far from any gravity source with the rocket engines off. No acceleration.
Wow. Okay, so gravity and acceleration are somehow two sides of the same coin. But how does that lead to the idea that light bends in a gravitational field? Light doesn't have mass.
Another great thought experiment. Back in the accelerating rocket, imagine you shine a flashlight beam straight across the cabin from one wall to the other.
Yeah.
From your perspective, inside the accelerating rocket, the beam travels straight. But because the rocket is accelerating upwards while the light is traveling across, the spot where the light hits the opposite wall will be slightly lower than where it started.
Because the wall moved up while the light was in transit.
Precisely. So to you, inside the accelerating rocket, the light beam appears to follow a curved path downwards.
Okay, I can see that in the accelerating rocket.
Now, invoke the principle of equivalence. If acceleration makes light appear to bend, and acceleration is indistinguishable from gravity,
then gravity must also bend light. Whoa! Even though light is massless.
it seems like a paradox based on Newton's view, where gravity only affected mass. But Einstein showed that gravity doesn't just interact with mass, it interacts with energy. And light, while massless, carries energy. EMC2 relates energy and mass after all. So gravity affects the path of light. Okay. Okay, my brain is stretching. So gravity isn't quite a force pulling things, it's related to acceleration, and it bends light. How does this all connect to the idea of gravity being curved spacetime? Back to the trampoline.
Exactly. The principle of equivalence is a huge clue that gravity isn't a force transmitted through space, but rather a feature of space-time itself. The presence of mass and energy actually warps the geometry of space-time around it.
This is a trampoline analogy again.
Yeah, it's the best simple visual, even with its flaws. Put a heavy bowling ball on a stretched rubber sheet. It creates a dip, a curve.
Right.
Now roll a small marble nearby. It doesn't roll towards the bowling ball because the ball is pulling it directly. It rolls towards it because it's following the curve, the slope in the rubber sheet created by the bowling ball.
So the planets orbiting the sun, they're not being pulled by the sun's gravity force in the old sense. They're just following the straightest possible path through the curved space-time that the sun's mass has created. That's the gist of Einstein's general relativity. Mass and energy tell space-time how to curve, and space-time curvature tells mass and energy how to move. It's the geometry itself. And yeah, apparently, even if you go on a diet and lose a little mass, you do infinitesimally flatten the space-time around you.
Huh. Okay, probably not enough to notice. Wow, so our common sense idea of gravity is just pull down, is really just us experiencing this underlying curvature of reality itself.
It is. It really highlights what we talked about at the start. Our everyday intuition is super useful for, not walking into walls, but it can be wildly misleading when we probe the deeper workings of the universe.
So what's the big takeaway for someone listening to this, trying to get their head around all this cosmic strangeness?
I think the key thing is just to recognize that what feels obvious or like common sense might just be a result of our limited perspective. This
Yeah.
should make us maybe a bit more humble and curious, willing to question those ingrained assumptions. And maybe consider what other things that we think are absolutely fundamental truths about reality might actually be far, far weirder than we currently imagine.
It really makes you wonder, doesn't it? What else are we getting wrong just because we haven't figured out how to look at it differently yet?
Exactly. This deep dive is really just scratching the surface. There's a whole universe of incredibly fascinating, bizarre ideas out there if you're willing to let go of common sense a little bit and just explore.
Definitely gives us something to think about. Thanks for navigating that mind-bending journey with us. Until next time, keep questioning.